Let's do more problems. On group actions. So here's a somewhat general principle which I am stating in the form of a problem here. So suppose I have a group action. So let G be a finite group acting on a finite set. Set X. Let's define the following map. Define for G in G a map phi sub G is now a map from X to X, okay, as follows via the following definition. Phi G, when it acts on an element X, it's just, well, when evaluated on the element X, it's just the action of G on X. Okay, so this is for all X in X. Okay, so define a map like this. Now, sort of many different things, then prove the following. So these are all things we need to prove. Number one, then this map phi sub G is in fact a bijection, Okay, and the set of all bijections we can, in other words, phi sub G belongs to, we call this perm of X, the set of all permutations of this finite set X, or the set of all bijections. And recall, the set of all bijections is a group in its own right by composition of maps. The map, let's call this map now as phi. The map phi from G to perm of X, which is each element G mapping to this G maps to phi sub G. This is a group homomorphism. Okay, and part 3 says, well, what's the, when you have a group homomorphism, you can talk about the kernel, which if you recall is a normal subgroup of G. Claim is that the kernel is nothing but the intersection of the stabilizers of all elements of X. Okay, so here are 3 assertions we need to prove. You can view this as just being another way of thinking about group actions. So let's prove these statements first. So each of them is rather easy. So if I have a map, if I have a group action, so what's given, I have a group action, okay, and I construct from the group action, I construct maps phi sub G, okay, defined like this. So first thing we need to show that phi sub G is a bijection, okay, and also that this is a group homomorphism. So let's prove the following fact. So proof. So let's prove first what is phi sub GH of X. So I claim phi sub GH of X is just the composition phi G phi H of X. Okay, so this is the first statement we'll prove, A. Okay, why is this? Well, this is more or less the definition of the action. So what is the left hand side now? The left hand side by definition was just the product GH acting on X. But if you remember, one of the axioms of the group action says that GH acting on X is just G acting on H acting on X, but that's exactly the right hand side, which is phi G evaluated on phi H of X by definition is exactly this. Okay, so this is done. Property B, phi sub identity of X. So the identity element, which I'll denote as 1 as we have done before, is, I claim, just X. In other words, phi sub the identity element of the group acts as the identity permutation of the set X. Okay, why is this true? Well, that's the another axiom of group actions, which is that so the left hand side here is just one acting on x, and by definition, I mean by the axiom, that's just x itself. So this is also true. Okay. So what does this imply? In particular, it says that, observe, if I take phi sub g inverse of x, or another way of rewriting the first axiom, phi sub g inverse is phi sub g composition phi sub a, instead of h I am putting g inverse, phi sub g inverse. Okay, so this is by a, special case in which I take h equals g inverse, but observe that this is just phi sub the identity, and part B says that this is just the identity map of x. Okay, this is identity of x is just the map which sends x to x for all x and x. Okay, this is an element of perm x, it's a map from x to x. Okay, so what does this mean? It says that if I take the composition of phi g with phi g inverse, I just get the identity. Okay, and similarly, similarly this is also equal to phi g inverse composition phi g. Okay, just repeat the same argument that I just did. Okay, so what does this give us? Why are we doing all this? Well, this says that the map phi sub g, in other words, phi sub g has a two-sided compositional inverse. Phi sub g has the following property, that when I compose it with this map phi g inverse on the left or on the right, it gives me back the identity map on x. Okay, what does that mean? It means phi sub g is a bijection, right? A bijection is exactly maps, I mean you can think of it as a map which has left or a right inverse, which has both left and right inverses. Here for finite sets, of course, you sort of, it's enough to check one, but from the more general point of view, let's just look at both. So we have phi sub g, phi sub g inverse is sort of the both the left and the right inverse of the map phi sub g. Okay, so it's a bijection. So that proves part A of the proposition. But in fact, along the way, we have proved all the other parts as well. So observe that, what did we need to prove? This is part 1 of the proposition is done, which says that phi sub g is a bijection. But in fact, we have also proved this, that it's a group homomorphism, because that's exactly these properties A and B. Okay, because it says that phi sub gh goes to phi g composition phi h. Okay, and phi sub identity goes to identity. So that's exactly the properties A and B exactly are the second point that we need to prove. Okay, so let's prove the last of the assertions, that the kernel of this map is just the intersection of the stabilizers. Okay, so let's see what is the kernel of this map. So I just now need to prove part 3 of this problem. To do this, I need to understand what the kernel of this map phi is. By definition, it's all those g in the group G such that phi sub g maps to the identity map. Okay, but what does that mean? That is, it's all those group elements G in G which have the property that G acting on x equals x for all x in the set x. Okay, but then observe, there's another way of thinking about this. I can say, let me fix an x in my set capital X, then a group element G which belongs to the kernel, so this G here, must satisfy the property that G stabilizes x, right? G x is x. Okay, so this means that this element G certainly belongs to the stabilizer G sub x. Okay, so this element x here, so G sub x, recall, is a stabilizer. G sub x is group elements which stabilize that fixed x. Okay, but then I want those group elements which stabilize x for every x in x. Well, that's another way of saying that this is just the intersection of all the stabilizers. Okay, so write this out in full by checking that, what I wrote here, this guy is a subset of this side, and conversely that the thing on the other side is a subset of this. Okay, so in any case, this is more or less from the definitions. Okay, so here's an interesting thing that we have formulated, that if you take the intersections of the stabilizers of all the elements of the set X, then what you get is actually a normal subgroup. Okay, because it is the kernel of a homomorphism. Okay, so recall this must necessarily be a normal subgroup. Okay, and this is sometimes a very useful construction. Okay, so that's the first problem, and the point here is that you can actually view actions rather here. So this part of the problem can often be thought of as an equivalent formulation of group actions. Okay, you can define, if you wish, a group action to be a homomorphism from the group G to the group of permutations of a set. Okay, let's move on to problem 2. Okay, which is the following. It says, suppose I have an action of a finite group on a set. So let G act on X. Okay, everything is finite here. G is finite, X is finite, and suppose X has cardinality at least 2. Okay, it's not a singleton, it's got at least 2 elements. Now if this action is transitive, which means that what does transitive mean? i.e., there exists a single orbit for this action. Every element of X is in the same orbit in some sense. They're all mutually, you can get one from the other by acting some group element. Okay, if the action is transitive, then prove that there exists at least one group element which has no fixed points, such that X G is empty. In other words, so recall X super G just means a set of fixed points. Okay, so which means G actually has no fixed points at all. Okay, again a rather interesting statement in some sense. It says that when a group acts transitively on a set, so of course this cannot be true if the set only has one element, because then that element is fixed by all elements of the group, okay, necessarily. But if you have at least 2 elements in your set and the group somehow acts transitively on this set, then at least some group element has to act in this interesting way, that it moves all elements of the set X. Okay, it doesn't fix any element, it moves all of them in some way. Okay, so let's prove this again. And to do this, we'll just use the orbit counting theorem again. Okay, so recall the orbit counting theorem, which says that the total number of orbits, so the number of orbits is the same as 1 by the cardinality of the group summation the cardinality of the fixed points. Now we have assumed that this is a transitive action, which means there is a single orbit. Okay, so now let me do also one thing. Let me move the cardinality G over to the other side. So there's only one orbit, so 1 into the cardinality of G therefore is the sum of the numbers of fixed points for all group elements. Now this is the equation we need to understand. Okay, now let's look at the left hand side. The left hand side is the cardinality of the group itself. The right hand side, how many summands are there, right? It's a sum of how many terms. Well, if the cardinality of the group is, let's call it some number, if the cardinality of the group is n, then the right hand side is a sum of n terms. Okay, so let's just give this a name. Let n be the cardinality of the group. then we observe that the right hand side is a sum of n terms. Okay. Now, what do we know about these n terms? They are all non-negative numbers. Okay, so it's a sum of n non-negative integers because it's the cardinality of the set of fixed points. So it's either 0, 1, 2, 3 and so on. So it's a sum of n non-negative integers. Okay. Now, when I sum up n non-negative integers and I have to get n as my answer, well, then what does it mean? Well, if all these guys on the right hand side are to be positive, okay, so suppose I argue by contradiction, why should there exist at least one group element whose fixed point set is empty? Suppose not. Suppose every element had some fixed point set, non-empty fixed point set. So let's argue by contradiction. If for all group elements G in G, the fixed point set is non-empty, what does it mean? Then all these summands on the right hand side that I talked about over here, right, was a sum of all these numbers. Each number is at least 1 because there is at least one fixed point. Okay, and if each number is at least 1, then since there are n terms on the right hand side, the right hand side is therefore at least, let's call this equation star, the right hand side of equation star, which means the right hand side of equation star will automatically be at least n because every summand contributes at least a 1. Okay, but recall the left hand side is exactly n, right? That's the cardinality of the group. Okay, now what does that mean? It means that every summand on the right hand side has to be exactly 1. That's the only way in which this equation can possibly hold. Okay, so is this I hope this argument is okay. All the summands on the right hand side are 1 or more, but 1 is the only possible choice, because even if one of them is 2, then the right hand side, the sum on the right hand side will become strictly bigger than n. Okay, but we know it has to equal n. Okay, so that's a very strong requirement. So it says that the fixed point set, if every group element has a fixed point, then every group element must have a unique fixed point. Okay, but this is already a problem because there is one very special element in the group, which is the identity itself. So let's take the identity element of the group. That guy has the following property, that what are the fixed points for the identity element? Well, the identity fixes every element of the set X, right? Recall the axiom for group action says the identity of the group acting on a set element X is X for all X in X, which means that every element is a fixed point of the identity. So that's what I've written like this. The fixed point set of the identity is the whole set X. Okay. So what does this statement therefore tell us? This means that since every fixed point set has cardinality exactly 1, this means that the set X itself must have cardinality 1. Okay, but that's a contradiction because we assume to begin with that, so contradicts our initial assumption that there are at least 2 elements in X. Okay, so therefore we approve this fact. So that's the proof that at least one element must act without any fixed points. Okay, now let's do one more problem which is very closely related to this one. So problem 3. So it says the following, suppose I take a group and I take, so let H subset of G be a proper subgroup. Okay, in fact for all this you don't even need finiteness for H and G and so on, but I mean if you wish you can assume that they're all finite. Let H subset of G be a proper subgroup, then the union of all the conjugates of H. Okay. So the union of the conjugates, which means I look at the subgroups GH, G inverse as G ranges over G. The union of the conjugates is also a proper subset of G. Okay, see the left hand side here is only a subset of G, but the assertion here is that this must still be a proper subset of G. You cannot somehow, by taking unions of conjugates, you cannot get every element of the group just from that. Okay, so let's try and prove this. This is seemingly nothing to do with group actions. Okay, it doesn't seem to be a problem about group actions, more a problem about subgroups and the group itself. But let's reformulate it into the language of group actions, and we'll see that in fact it's actually the previous problem in disguise. Okay, it's going to involve the previous problem, which is problem 2. Okay, so let's do this. So to do this, we first have to construct a group action. Okay, so I'm going to take the action of a group G, of the given group G on a set X. So how will I construct this set X? So here's the first thing to note. I will define this set X as follows. I take the set, which I will denote G mod H. So H is not a normal subgroup here. So when I say G mod H, I don't mean it's not a group or anything, but I can think of it as a set. Certainly this is just the set of all left cosets. So this is all sigma H as sigma ranges over G. So this is just the set of all left cosets. Okay, thought of only as a set, but in fact it's a set on which the group G acts. Okay, that's the interesting bit. What's the action? Well, the most natural thing, if I take a group element G in G and I take an element from X. What's an element of X? Well, it's a left coset. Well, how do I make it act? I just say it's a new left coset, the left coset of the element G sigma. Okay, so it's easy to check that this is a well-defined. So well-definedness, remember, comes up because in some sense I am choosing a representative of my coset while writing this definition, but it doesn't depend on which representative I pick of the coset. So this is well defined and in fact is a group action, is an action. Okay, so I leave these two for you to check. Exercise, please do check that this is a well defined action of the group G on this set X of left cosets. Okay, now I have an action. Now let's try to figure out what the properties of this action are. So I claim the first property is that this is actually a transitive action. In other words, what are the orbits? Well, there is a single orbit. Everything is in the same orbit. So how do we prove this? Well, the easiest is to say let's pick a particular coset. Let's take this special coset H. So look at this element H, which is a coset inside my set X. It's a single element. I claim that every other coset can be obtained from this particular special coset by a suitable action of a group element. Well, how do I do that? It's more or less from the definition itself. What do other cosets look like? Any other coset looks like sigma H. Every coset looks like this. Now, how do I get sigma H from H? Well, if you just see what this definition is, all it says is you just multiply on the left by the appropriate group element. So this I can get sigma H from H by acting by sigma, because sigma acting on H. So here it means I'm sort of picking identity as my representative of H, if you wish. So sigma acting on identity H is just sigma H by definition. Okay, so what does that mean? It means that every coset lives in the orbit of this element H, which means that the orbit under this group action G for this element H is in fact the whole set X. Okay, so therefore it's a transitive action. There is only a single orbit Okay. Now I'm going to use my my previous statement. So I'm going to use my previous problem. So let me just recall what the statement of the previous problem was. I needed a group acting on a set X. The cardinality of the set X has to be at least 2, and if this action is transitive, then we needed to prove that then we proved that there is at least some group element which has no fixed points. Okay, so let's verify the hypothesis. First, we have checked it's transitive. The second hypothesis I need is to check that the cardinality of the group of the set X is at least 2, but observe the cardinality of the set X is nothing but the cardinality or the index of H in G, if you wish. Okay, the number of cosets, and that's just cardinality of G by H when they're all finite. And I've assumed that H is a proper subgroup of G, so which means that this is at least 2 since H is assumed to be proper. Okay, so the second hypothesis is also there, it's also satisfied. Okay, now let's apply the previous problem. Let's apply the previous problem. What does that allow us to conclude? We conclude therefore that, so the conclusion of the previous problem was the following, that there is at least one group element, there exists an element G in G whose fixed point set is empty. Okay, now let's see what that means for this particular action. So this means that so what is the fixed point set for G? So this is for all, so fixed point set, so which means for all cosets, for all sigma H in X, for all cosets, G does not fix that element. Okay, this is another way of saying that the fixed point set is empty. I'm just rewriting it as saying that for every element of X, G does not fix that element. Okay, G maps that coset to a different coset. Well, what does this statement mean in terms of cosets? It says that if G sigma H is not sigma H, this means that, so I can push the sigma over to the other side. This says sigma inverse G sigma is not an element of H. Okay, and remember this is for all sigma in the group G, if you wish, right? This is for all cosets, so this is true for all sigma in the group G. That sigma inverse G sigma is not in H. Now again, this last equation can be written rewritten again. I can push the sigmas over to the other side. This says that G is not an element of sigma H sigma inverse. Again, this is true for all sigma in G. Okay, and now the last conclusion, let's stare at that a little harder. So it says that this particular special element G, which has no fixed points, that works out to the same thing as saying that G does not belong to sigma H sigma inverse, this particular conjugate of H, for every sigma in G. Okay, which means G doesn't belong to the union of all the conjugates of H. Okay, and that was exactly what we needed to prove, because we have concluded that there exists a group element which doesn't belong to the union of all the conjugates. Okay, now if you look back on the statement of the problem, we need to say the union of all the conjugates cannot give you the entire group G. It's a proper subset. There is at least one element which lies outside this set, and that's exactly what we have produced. Okay, so that completes this problem. Okay.